Looks like we also have the live stream. Woohoo, everything works. How have you been the last 2 weeks? Busy?
Good.
Good? Help refresh. I'm not a fan of formal proofs. The good thing about formal proofs is that they're kind of rigorous and you're sure that it's correct afterwards. I guess nobody loves them for their own sake. It's just if you don't spell things out, you're never quite sure if it's correct. The symbols in the language is something you can learn. Also, it's not so important. You can be just as precise with English or any natural language. It's just harder. You have to be very disciplined of using language that's so clear and unambiguous that it does the same as the formal symbols. But you could do it. So I hope that all the groups that submitted received some instructions on how to do this peer review. Each been assigned different groups so that if everything works out, every group should get also 3 reviews from other groups with some hopefully instructive feedback. And of course the whole thing was also a bit of a fun way of exploring how scientific publications are looked at. There you get the same setup that different people look at it and write a little report. Some of them are more thoughtful than others, and you often get around 3, and then there's some decision made based on those. The decision in this case is kind of imaginary. But I wanted to force you to make a final verdict at the end. That's why this question about publication is in this review form. I suppose the mic is again on the live stream. The thing is, if I'm speaking here, it's showing us almost reaching the max. So my feeling is if I make it louder, it will get cracky on the recording. Okay, maybe I have to play for next time with amplifying the audio after the recording a bit. That might work. So for the live stream, there's some filters. Yeah, I hope it works by just turning up the volume. Okay, a bit of organizational things. So this week you're still busy with these peer reviews. We'll start with normal tutorials and exercise sheets also starting this week, so there will be a sheet released tomorrow. And then we'll have roughly a week to work on that. The first one has a few more things just to practice again. I'll try to keep them somewhat lean in the future. And then from next week onwards, we'll have some extra session where we discuss some of the solutions of these exercise problems. So you'll hand them in and you get some feedback on your solution. And we'll have one central session where we discuss some solutions. So watch your emails. I'll send around some suggestions for when to do that. I hope we find a slot that works for most or everyone. Specifically, like how many people would have time at some point Tuesday afternoon? Do you have lecture slots or other regular things? Pardon?
Next week?
All the weeks, starting from next week.
Exactly at what time?
Up for discussion, like
4 would be fine.
4 p.m. on Tuesday.
You can maybe start a poll on Ilias, because I'm good with all times.
Yeah. Well, if it's as easy as trying 4 p.m., we could go from there. I'll email around so that everyone has a chance to chip in. I wanted to continue a bit with a few remarks from what we covered in the first week. Maybe a tiny recap. I don't want to go through all this again. We've discussed what P and NP is a bit more formally. So we introduced these Turing machines as a specific model of computation that for our purposes is expressive enough, and we defined these classes P and NP. Now, jumping somewhere in the middle, okay, random access machines was the first model, and Turing machines in more detail and how they compute. But the important point that all the problems that we look at are really languages where we just have a yes-no decision. We'll come back today. And this I wanted to show again. So the time on a specific input size is the worst over all inputs of that length. And remember, when we say size of the input or length of the input, it's always the encoding. You have to specify an input as a string that you can feed to this Turing machine. So here's always clear what that means. It's just over this alphabet. Okay. And then the class P was all the problems where we have some polynomial time algorithm. In the worst case, we can decide yes or no in polynomial time. And the class NP was the same, but we allow a non-deterministic Turing machine. That was maybe somewhat unintuitive, but we had this alternative point of view using verification, where if you have a verifier that's given some input and a proof, a certificate for that element to be in the language, then it can verify this polynomial time. That's the same as the class NP. This lengthy proof that we've done. And then the last bit was the theory of NP hardness, or NP completeness. Right, just wanted to show that definition again. That was the key definition, to relate one problem to another in terms of its hardness. And here we say we reduce some language to another language. If there's an algorithm that takes inputs for one language, a W that could be in A, and transforms it into a different input, a different string that could be in B. And the reduction has to be so that this equality holds, or this equivalence holds. W is in A exactly when the transformed string is in B. And then you've spent some time doing such specific reductions. I'll skip over this now. Okay. That's basically where we're at. Just to get the notation on record, let me very briefly go through these problems again. In this section, I'll briefly introduce some of these problems that you've seen and used before, but just so that they're given with some specific notation that we can refer to. I hope I've been consistent whenever I use them. So dominating set is you're given a graph and you cover all the vertices by picking vertices, a subset of vertices, so that every vertex is either picked or one of its neighbors is picked. A Hamiltonian cycle means a path in a vertex that visits every vertex exactly once. So there's two versions, directed and undirected, depending on whether the graph has direction on the edges. These are all part of the classic problems that you worked on, or some of you worked on. Click is, can you find in a graph a complete subgraph of a certain size where all possible edges are there? An independent set is the opposite. Can you find an empty subgraph of a certain size? Then we had the traveling salesperson problem, which appeared earlier on, so I don't want to repeat the definition. We'll come back to that in the next chapter. And then graph coloring is it's a problem where, again, given some graph, and we have to assign colors to the vertices so that none of the edges have the same color on the two endpoints. And the question is, can we do this with a certain number of colors? Set cover is a problem that will come back to us at some point later. We're given subsets of a universe, and we try to cover the entire universe. We have to pick subsets so that all elements are covered. And the question is, can we find a small enough selection? There's a weighted version where the sets have specific costs, and then the question is, can you do it with a bound on the cost? This is actually a general theme that you will see in many problems. There's often a combinatorial version where the cost is just the number of things, and then there's a weighted version where the cost is the sum of the costs of the elements you select. And oftentimes, the two are very similar. It's often the case that both are hard or both are easy. I mean, one example where both are easy is shortest paths in graphs. If you have a graph that's unweighted, then this is just breadth first search, and you find the shortest paths by number of edges. And if the edges have weights, then you know algorithms for that as well. Either Dijkstra's algorithm if the edges are non-negative, or Bellman-Ford. Then you can find the shortest paths by the sum of edge weights. Right, in this case, both problems are in P. They're efficiently solvable. A problem that's a bit different from the others we've previously seen is this one, closest string. Here we're given a collection of strings of the same length. And the question is, can you find some other string that has Hamming distance at most k to each of those strings? And Hamming distance just means how many characters are different. So you count how many mismatches you have. And that's also a hard problem. We might come back to this at some later point. MaxCat is, again, in a graph. Can you distribute the vertices into two sides, a left and a right, or a set S and T, so that the number of edges that go across the cut have one endpoint in one set and the other in the other set is maximized, or is above a certain threshold. And we know that the converse problem, minimum cut, is a problem in P. It's efficiently solvable. That's the famous max flow min cut that you may have seen in algorithms classes. But if you flip around the problem and you ask for a cut with many edges across the cut, it's a hard problem. And last one is, again, famous calc problem, exact cover. It's similar to set cover. You have subsets of some universe, and you want to cover all of the elements in the universe, but this time you're supposed to cover each element only once. So the sets have to be disjoint as well. Any questions on those problems? Many will be familiar, like you've had those before. As I said, I just wanted to have a canonical definition that we can refer to if we use those problems or those names. Of course, there's many more problems and many more NP-hard problems. In particular, this book on computers and intractability, Gary Johnson, has hundreds of problems that are known to be NP-hard, or NP-complete in many cases. I think all those problems are NP-complete. But we don't need all those problems here. Yeah.
How is Hamiltonian cycle different from traveling salesperson?
Yeah. So the traveling salesperson problem, I didn't go over the definition properly, but we'll actually need it in the next section, so maybe it's good to revisit. Here the input is a complete graph, but it has weights on the edges. So in a way, you could say TSP is a weighted version of the Hamiltonian path problem, where the Hamiltonian path has a graph without weights. There's either an edge or not an edge between two vertices, and you're trying to find some round trip, but you can only use existing edges. And TSP, all the edges are in principle there, although you could put the cost of an edge so high that it's effectively not usable anywhere. But in principle, all the connections are there, but they have different costs, and so the question is to find the shortest round trip, or one that's below a threshold. Yeah, that was a good question. But the problems still feel very similar, right? They're closely related. This will come back actually. Okay. Other questions about the problems? There's a few more that have a slightly more numerical flavor. Subset sum is given a list of integers and asks if there is a selection of those that sum to exactly 0. So here these are positive or negative. You can, I guess we technically haven't defined for our Turing machines how we deal with negative numbers, but I guess you can imagine there's a minus in front and you have to adjust how the arithmetic works. You could also formulate the problem with giving a specific value that you're trying to match. But this, I found this one surprising when I first learned about it. So just a collection of numbers, why should it be hard to find some subset that sums to a certain value? But it's also a hard problem. You can do reductions. The knapsack problem, we'll see later again, is given a collection of items. So these items 1 up to n, they have a weight and they have a value, and you're trying to fit as much value in your knapsack, but you can't exceed the weight bound. So the collection of items that you select has to sum in weight to at most a certain threshold, and you're trying to achieve at least value k. Bin packing is also given items, but here we only have weights and some capacity for bins, and we're trying to put the items into as few bins as possible. So here the way I formalized it here is you assign the elements to 1 out of k bins, and then in each bin you have to sum to at most the capacity. For most of these problems, there's an optimization version and the decision version. We'll come back to that. And the last one, this might also be a good question. This will come back in many cases. Who has done some course on linear programs and linear optimization, LPs and ILPs? Has anyone seen that ish? Okay, then maybe it's worth spending some time on this in another chapter. It's a beautiful piece of theory or applied mathematics, or I don't know what you want to call it. It's often done as part of operations research. So more business-oriented studies often do a little bit of that, because it's a standard tool that you can use to optimize business processes, production, and so on. But it's also a great algorithmic tool. Okay, so I'll plan a little bit on that. For this problem, maybe this sounds a bit weird then for you, but the definition, I guess, is easy. You're given some matrices or vectors of numbers, this matrix A and a vector B and another vector C and some threshold. And the question is, can you find a vector of zeros and ones? So that here, this is a matrix vector product. Standard linear algebra comes haunting us again. So you multiply this vector on the matrix, and you get back a vector. And so this less or equal is intended to be element-wise less or equal. Right? The first entry of the vectors should be smaller, second, and so on. So this is essentially a system of linear inequalities. That's what that says. So you're trying to find some vector x that satisfies a system of linear inequalities and has a dot product with this other vector c that's above a threshold. So the theory of linear optimization, these are side conditions, maybe capacities of some machines that you cannot exceed, and this is somehow the gain or the reward you get, your profit, and x is some way you can have a decision, do it here or do it there. We'll come back to this then. Okay. But as an abstract question, this is also an NP-hard problem if you're trying to find these 0, 1 vectors that satisfy these inequalities. Okay, that should be all. Questions on the second set of problems, more integer-related ones. Okay. In the last section here, I want to come back a little bit to the different notions of problems that we've been talking about. When I was explaining the problems in the last section, you may already have seen that sometimes I didn't explain what's on the slide, but I explained the more intuitive optimization version. And so let's pull that straight, because this is something that's often relevant, and there's a few little details to point out to make sure that we can deal with optimization problems in the same way. So far, everything has to be a decision version. A problem was a language, and then something can be in the language or not. Or to say the same thing, you're given an input, and you can say yes or no. It does make sense to also define the more general problems where we try to find the best possible solution. For the hardness theory, we'll stick with the decision versions, but there's an easy way to put the problems into context and connect them, and that's what I want to do in this part. So formally, an optimization problem has a bunch of different components. There's an input alphabet. We somehow have to encode the input again. But this time we also produce an output. So we also have to say how that looks like. Then there's a certain language over this input alphabet of allowable instances. So these are valid encodings of some problem. Again, if we want to make this more concrete, say we look at TSP as our running example again, then the allowable instances would be distance matrices. And the input alphabet would be some way to encode the distance matrices. Maybe it's just a binary alphabet and we write down the numbers in binary. Maybe we allow a third symbol to say this is the end of one number and the beginning of the next. Makes it a bit easier to read. Then maybe not all of these instances are really relevant for this problem. I guess for TSP, the two would be the same, but maybe you want to restrict TSP to a certain variant. To make this clear here, let me say it's metric TSP, where the distances have to satisfy the triangle inequality. So it has to be, when you go, metric means if you have cities here, A, B, C, and you go from A to B, that cannot take you longer than going from A to C and then to B. So the distance from A to B should be at most the distance to go via C, the detour. Okay? This is a very natural condition, but if you just specify a matrix of numbers, this is not guaranteed, right? It may not be satisfied. I didn't want to zoom. Okay, so in general, this may be violated, but let's suppose we look at metric TSP where we only allow instances that satisfy this. So the actual problem instances would be metric distance matrices. And again, some encoding thereof. And now you already see we need some way of checking that something is an actual instance. Then we have this function n that tells us what are possible solutions for a given instance. And these have to be defined for all of the allowable instances. So for TSP, this would be all possible round trips, so permutations of the cities. Okay. And then we have a cost function, which given some allowable problem instance and a solution, where this is one of the possible solutions, tells us what's the cost of this. And I keep the terminology neutral because we can use the same for minimizing and maximization. Now cost sounds like you want to minimize, but well, depends whose cost, I guess. The important bit is this has to be a function that's computable. We'll come to that. So this is, so far, this is a general definition for any kind of optimization problem. There's no mention at this point about efficiency and how fast we can do things, okay? Okay, in general, this cost function can be any real number. Now, good luck with representing exact real numbers on your Turing machine, so probably it will be rational or maybe even an integer. Okay, and the goal is minimization or maximization. Is that clear so far? Now, in general, this is a very broad definition. What does it mean to solve such a problem? We're given such an optimization problem, then we say that a solution, some y in the solution set for x is optimal if the cost of this specific y minimizes or maximizes, depending on the problem, right? Goal is this part of the input. Minimizes or maximizes the cost among all possible solutions for this instance. That's the very natural definition, okay? An optimal solution is one that minimizes cost if you're minimizing and maximizes reward if you're maximizing. Okay, we'll always deal with consistent algorithms. An algorithm is consistent with an optimization problem if it always outputs something that is an allowable solution for this instance. Again, in principle, if you specify an arbitrary program, it might do whatever nonsense. We're not usually interested in this. So consistent means it has to be in this set of possible solutions. But the important bit is an algorithm solves this optimization problem if it's consistent and it all outputs the optimal solution for all instances. Okay? And here, let me stress again, we're only requiring this for the actual instances. Okay. We've seen many examples in the list previously where we had a threshold, usually called k. And if you say, I'm not giving you this threshold, but I'm asking for the best possible solution, then you naturally get an optimization problem for many of the problems we've seen before. And we can very briefly run through back. Closest string, you can ask what's the smallest k so that you can find a string satisfying this. Max cut, you optimize for the many number of edges. Here you want to maximize. Exact cover is different. There's not really a question of maximization. Maybe you can ask for the fewest elements, but this problem remains hard if it's as is. TSP, of course, you can minimize the cost of the tour. You can minimize the number of colors you need for graph coloring, minimize the number of sets in set cover, and minimize the cost. Dominating set. So most problems are actually like this, that they're optimization problems. Hamiltonian cycle is an exception, and exact cover is an exception. All the others are optimization problems naturally. Here's a somewhat less immediate example, but one that will also come back at some point. The maximum satisfiability problem. It's a bit awkward, but it has technical reasons why it's useful to look at. So let me introduce it here. We're given a CNF formula, so conjunctive normal form. This popped up earlier, but I skipped over that part, so let me say it again here. It's a Boolean formula, so something comprised of variables and or not conjunctions. But it has a specific form. Here it's one big and of different parts. And then each of these clauses, each CI is some xi or not xj or xk and so on. You remember 3SAT was exactly 3 of these variables or literals. If we just say CNF, it's unrestricted. And the total number of variables is n. Now maxsat asks to satisfy as many of the clauses as possible. Normal satisfiability means all need to be satisfied because we take the and. But here we're asking just to satisfy as many as possible. So formally this would be the allowable and actual instances are all the encodings of such formulas, maybe listing the clauses in some form. Then solutions are assignments of all the variables, so you can write them down as 0, 1 strings, where the ith position gives you the value of the ith variable. And then the cost of a combination of an input and a solution is the number of clauses that are satisfied. Here's really a reward, not a cost, right? Because we maximize. Okay, is the problem clear? As a Boolean formula, this is a bit nonsensical. Like either the formula is true or not. It doesn't help to satisfy all but one clauses. But let's pretend it's still useful, and it'll come up as a reduction partner later. Yep.
This is in conjunctive normal form, and we are finding next set, and everything is an and. How can others not be true and be correct?
Yeah, that's what I said. As a Boolean formula, it doesn't make sense. But you can still define, I want to satisfy at least as many of the clauses. Again, it's a bit of an artificial problem. But it turns out it has, forget about the meaning of the formula. Maybe it's just different conditions, and you'd like to at least meet as many of them. If it's not possible to satisfy everyone, you want to make as many people happy as possible. But it's a bit unnatural, but turns out to be a useful intermediate problem. Okay, so far optimization problems were very general. Now let's try to pin down the efficiency. Do we have NP first? Yeah. Okay, so the first restriction is the equivalent of NP, and NPO is the equivalent optimization problems class. So these are optimization problems where, first of all, I can efficiently decide whether an instance is one that I'm actually interested in. So these were the actual instances. If you give me something, I can't even efficiently tell whether I'm supposed to solve it, it's a bit pointless. So formally, this is in P. And second, there must be an efficient way to decide whether something is a solution. So there's some polynomial, and for every allowable instance and for every possible solution, first of all, the solution shouldn't be too big. If I were asked to produce solutions that are exponentially long, there's no way I'm going to do that efficiently. And secondly, there should be an algorithm that decides for all short enough strings whether or not that is a valid solution. That's also just a sanity check, really. So if someone claims here's a TSP input and here's a round trip, you should at least be able to check whether the round trip is a correct permutation of the cities. Otherwise, we're completely lost. But these are still very weak requirements. The last one is also important. The cost has to be efficient to be computed. So again, polynomial time. Also very natural. If I can't, given some input, tell you how costly it is, how am I supposed to optimize for it? Okay, so these are all very weak requirements. And that's all for a problem to be an NPO. In particular, it tells you nothing about how to find the solution, but that's the same for problems in NP. The problems where we have a chance to solve them is this class PO. So here it's everything that NPO requires, all of these three, plus there should be an algorithm that in polynomial time computes an optimal solution. Okay, and then together with these, I can also verify that it's indeed optimal if I'm asked to. I think most of the definitions is very natural, is what you would think. NPO is all the problems where I can at least verify that the solution is correct if you give me the solution already. And PO is the ones where I can find it efficiently without being requiring your help to start. So it's not very surprising how these things are formalized, but I think it's worth doing so that, for example, you don't forget that the cost has to be efficiently evaluable and so on. It's easy sometimes to write down a problem that sounds enticing to solve, but there's not even in NPO because you can't even compute the cost, for example. Okay. At this point, I think it's worth recapping the different types of problems we had. Specifically because we had the Turing machines with their languages and NP in the original definition, but then also this VP definition. And now we have optimization problems. So I would organize this as what is the output? Either we just do a single value, yes or no, or we have to provide a solution or a certificate. And the other axis is whether we're checking a given threshold or whether we have to find the optimal value. And so what we've just defined would be the bottom right. These are optimization problems. I'm given nothing, but I'm supposed to find the optimal value myself and also provide a certificate, a solution alongside with it. Right? Now, the other extreme was the decision problems. This is where we started. That's the same as languages. So here we're just given a string and we asked yes, no. Now we've also had this corner below here, which is sometimes called the search problem. So this is effectively what we wanted for VP. I'm still asking a yes/no question, but instead of, VP requires this as input. Instead of just claiming yes/no, I'm supposed to prove that my answer is correct. And so you could say this is the problem in satisfiability. I'm asked a yes/no question, is the formula satisfiable? And then the decision problem, I said yes, and you were happy with that. Now in the search problem, I say yes, and then you ask me, okay, fine, what's the satisfying assignment? Okay. And this corresponds to the optimization problem, how we defined it on the previous slides, where I'm also supposed to provide you with the concrete answer. And then the last bit also sometimes makes sense to talk about. And that's often then called the evaluation problem. That's an optimization problem. You're not actually interested in finding the optimal solution itself. You're just asking for the threshold. What's the best possible cost that you can achieve? But I don't have to provide you a proof. I don't have to provide you with the solution itself. Okay? And so the reason why I'm drawing this matrix is that you can go from one collection of problems to the other. And some directions are easy. For example, you can always go this direction essentially by using that the cost function is efficiently computable, and otherwise by essentially forgetting the certificate. Right? That's easy. If you can solve one of the bottom row, you can solve the top row by just not outputting the certificate. The interesting question is whether you can go top down. The other thing you can also do very easily is this direction. Otherwise, it's easy. Right, if I'm given a threshold and I can find the optimal value, I just check the optimal value against the threshold and output whether it's better or not. The interesting bits are, can I go from left to right? And then you can basically always do a binary search for the right cutoff point. So you can use as a black box that you can decide whether something is above or below the threshold. You can use a binary search on the numbers that make up the cost function to at least get us as close to the optimal value as possible. And if the cost function is efficiently computable, it can't be an arbitrary real number. So you'll have to converge eventually. It's also true because the number of possible solutions is not arbitrary. They have to be bounded in size, right? So this works, and even though the search space is very big, is exponential, you're taking binary search, you're taking the log of the search space. So that's back to polynomial. So that's actually a general reduction, specifically if the costs are discrete. Now, an interesting question is whether you can go from top down, from thresholds, from the single value, from decision to search. And in general, it seems this is not always possible. But it for any concrete problem you look at, it seems usually easy. So you look at this on the tutorial sheet. But most of the time you can do it. So if you put this together, by and large, all four corners are not as far away from each other. For most problems, the complexity of those four corners is the same in terms of polynomial versus exponential. Okay. Questions on this terminology? Is that clear? There's even some, depending on who teaches undergraduate modules, sometimes people work everything from search problems. I don't know if anyone has experienced that. It's not so commonly done. Okay. A few of these things, there's a few definitions that formalize some of what I've just said. I'll go over those a bit more quickly. So if we have an optimization problem in the way we've defined it before, then let's denote, this is I guess in general, so worth pointing out. I'll write opt subscript the problem and then an input, so an instance x, with the value of the optimal cost. Then we can define threshold languages, which is turning an optimization problem into a decision problem by using pairs of an input and a value, a threshold. And then you include in the language all the pairs where the optimal value is better than the thresholds. And you have these two distinctions for min and max. The only thing here worth pointing out, k subscript 2, this is supposed to mean the string k is a binary string. And so I'm just reading this as a binary number. Okay. I think here I'm assuming that the cost is an integer to make life a bit easier. So is it clear what the threshold language is? You take an optimization problem and you turn it into the threshold language by taking all the pairs of instances and the threshold where the optimal value is better than the threshold. Okay. We say such an optimization problem now is NP-hard when this threshold language is NP-hard. Formally, we have only defined NP-hardness for languages. That's why we need this definition to lift it to optimization problems. And it's not hard to prove that then if you have an optimization problem, which is the other way around, if the threshold language is NP-hard and we assume, as usual, P is not equals NP, then the optimization problem cannot be efficiently solvable. Okay? Intuitive statement, I guess. But let's briefly spell out the proof. We prove this by contraposition, so assume that U would be efficiently solvable. Then we have a polynomial time algorithm that computes the optimal solution in all cases for all instances, right? In particular, we can compute the optimal value of that solution because cost is computable. And that means we can decide whether the optimal value is better than any threshold in polynomial time. So we've decided whether the language, whether an element is in the language. That means the threshold language is in P. But if the language is NP-hard and is in P, that means P equals NP, which is a contradiction to our assumption. That's what we had this one for all for one lemma and earlier in this unit. So that means lang U cannot be NP-hard. That's a contradiction, so U cannot have been in PO. Okay? So it just means that if the threshold language is NP hard, the optimization problem will not be efficiently solvable. It's one of the easy directions in the table. And as a concrete example, we can show that this max SAT problem is NP hard. And also here, formally, we can do a reduction to the threshold problem. So just to spell that out once, we take the 3-SAT problem, a known NP hard problem that we've worked on before, NP complete problem, and we reduce it to this threshold language for max SAT. And this is actually very easy because it's kind of a special case of max SAT if you look at it. So given any 3-SAT instance X, and suppose it has m clauses, then we just produce this pair X, M, which means, can I satisfy all clauses in my formula? That's exactly satisfiability. So the rest is kind of just this chain of equivalences. X is a 3-SAT, is a yes instance, if and only if it's satisfiable, which means all of its clauses, m clauses, are satisfiable. That means xm is in the threshold language. Okay. That's a tiny and very simple example of how you can use this definition to prove that optimization problems are NP hard. So that we can talk about those being NP hard, not just the threshold languages or decision problems. That's an alternative. Most of the time we'll be happy with just proving that the decision version is hard and that the optimization version is then even harder, is kind of proven once for all. Okay, let's wrap up this intro section. Much of this supposedly is covered in some undergrad TCS modules. Maybe not in the same kind of form of setup. So we formalized what it means to have a polytime algorithm, which we call efficient. We've looked at decision problems and these other forms of problems, Turing machines as a way to compute things, and we showed how we can establish this theory of intractability. So we can now rigorously prove that some problems are NP hard, which means they probably don't have a solution. But we set out to kind of solve problems despite this fact, right? This was all a prelude to what do we do now? And so let's get started with that part. I guess before we do that, let's have a few minutes break, and then we'll start with the first type of solutions for hard problems. These are your 5 minutes. Chat as loud as you want. Up to you. Also, if you have any questions, it's also an opportunity to discuss stuff. I've seen some. I don't know if you fixed it. Meanwhile, I've immediately seen that some groups only submitted a video and no written report. Maybe double check if you submitted both. And if not, let me know. Then we can maybe open up the submission again so you can add that.
I was gonna ask, is the time and location is the time and location set for your seminar, Space Efficient Computation?
The kickoff meeting is set. Let me check. Yeah, so 22nd, 11 a.m.
Okay.
Are you on the Elias course for that?
Yeah, I am.
Okay.
But I didn't receive any email, or maybe
Huh.
I didn't see it.
Yeah, check again. I meant to send it via Elias, but if it didn't come through, I'll check it. I also put it on the Elias page now, so it's there. Yeah. I mean, I'm trying to expand the list of topics a bit, but I think more than a dozen people doesn't make sense because we want to see the talks as well. So I'll see how many people will show up. Maybe some people have found different seminars meanwhile, but the initial interest was huge.
Pretty late, so that might be.
Yeah. Well, my experience with seminars is that people don't start the first few weeks anyways on working on the topics. And we have time to push it into the term break. Okay, let's slowly continue. I want to ask some question up front, because that will come up. So without much further context.
I'm between 1 and 2, like.
Between 1 and 2? Yeah. Hey, come back. Lost connection. It seems to work. Okay, we're tied for all options. Well, if you know dynamic programming, you may know that the name is just as silly as it can get. Mostly invented for political reasons to justify working on math. And it predates the modern way of using programming to write code in bits. Okay. So somewhere all over the place. we don't need a ton about it. It's just an example that follows this design pattern. You can follow the design pattern without having seen dynamic programming before, but if you've seen it before, the example might be much easier. In Unit 3, we'll look at pseudo-polynomial algorithms. The first example of something where we can take an NP-hard problem and still do something about it, at least for some problems. And this will be a relatively short unit. There's not a lot of deep theory in there, but it's a cute observation and is a good segue into the next unit. So we'll start with a little bit of a definition just to set the stage. This is a lightweight and slightly vague definition. An integer input problem. It's just some problem. Can be an optimization problem or it can be a decision problem, where part of the input, the instance, consists of numbers. So formally you could say it's some arbitrary string and then a sequence of integers. All that we really need here is that for a given input, I can say what's the largest integer that occurs as part of this instance. So again, we've seen some examples before, and if we pick TSP as the prime example, maxint would just be the largest distance that occurs in your distance matrix. So simple definition. The point of this is just not all problems are integer input problems. Sometimes the input is all about strings. Say this closest string problem where I'm giving a list of strings and okay, there's how many differences do you allow? But if you say the optimization problem of that, then the input would just be strings, then there's no integer associated with that. Now as a warm-up, let's think about how big or small this maxint can really be. Because that will determine how hard we have to work in the following. Okay, I'll switch over. Yeah, just about fit all on the slide. I guess 11 people is mostly it, so here's your votes. And you can select more than one answer. And because these are big O bounds, many of them are true. Let's discuss this briefly. So all of these are possible as how big maxint can be as a function. So the extreme case clearly is that my input is just a single big integer. Okay. Then it could be still a tiny number if I somehow prepend it with lots of zeros, or maybe it's not the only thing in the input. It could be really small. What's the largest it can possibly get? I can use all the space I have for digits of a number. I could certainly write down 2 to the n. 1 with n zeros, something like that. Now I can do slightly bigger because in general my input alphabet isn't restricted to binary. And so I can effectively achieve, so this constant in the exponent is just transforming the basis to a different constant. This is essentially c to the n for any c, for any constant c. And by using a larger alphabet, I can achieve that. It's a bit cheating in the sense that we think of n as being the same, independent what the alphabet is, but the Turing machines always force the alphabet to be constant size. So in a way, it's okay, but you can debate about this, and maybe it's enough to do binary numbers, especially because I put binary here on the slide. So it's maybe a bit unfair. But clearly there's an upper bound. You cannot go above that. So also this max int cannot be arbitrarily bad. Okay, it can, for example, not be doubly exponential, and is certainly always bounded in terms of the input size. By the way, if you're wondering how to specify an integer without telling you up front how many digits it uses, there's a nice solution that some of you have seen in efficient algorithms. Suffice it to say, it's possible, even if you just have binary alphabets. Of course, with more alphabets, it's easier. You just put a special symbol as end of number. Okay, so still, it could be exponential. That's the point, which means if some algorithm has a running time that depends on max int, it might be an exponential time algorithm. Nevertheless, we'll do the following definition. We call an algorithm pseudo-polynomial if its running time is a polynomial of the size of the input, n, and this max integer. So in particular, this means that the overall thing could be exponential. So pseudo-polynomial time does not mean polynomial time, right? That's quite clear. That's why it's only pseudo-polynomial. Now maybe this term is not great. And there's another term, quasi-polynomial, which means something entirely different. I just put it there so you're not confused. It will not pop up in this lecture, but in this module. If you just vaguely remember, it was something like polynomial. The term is not super great. It's not quite polynomial. But why do we call it pseudo-polynomial? At least it has some form of polynomiality if this max int is small. Right? That's where the name comes from, I suppose. Specifically, if we can bound max int by some polynomial in the input size, then the overall thing is also a polynomial, a different polynomial. That's just because if you insert, say, max int of x is, and we use n as the length, right? Maybe this is less than n to the 10th, right? And then maybe this p is, I guess, two variables, n and m, is less than n times m to the 5th. Then if you insert this for m, n times n to the 10th to the 5th is a lot. but it's not infinite. It's n to the 55. N to the power 55 is not a running time that we would like for any practical algorithm, but it's polynomial. What I'm saying here is, if you insert one polynomial into another polynomial as one of its variables, it remains a polynomial, just of different degree. So, if maxint is bounded by a polynomial, a pseudo-polynomial time algorithm is actually polynomial time. Okay. To grab this formula, there's another definition. We take a problem, u, and we take a bound on the maximal integers that are allowed. And then we say value of this bound, subscript u, is a new problem, but one where I'm only allowed to use inputs where the max int is small, smaller than h. Okay? So think of all the TSP instances where the distances are at most 10, or a function of the input size, at most square root n. That's up to you. And then we can have this this little theorem. We have an integer input problem, and we have a pseudo-polynomial algorithm for this problem, assume that exists. Then indeed, for every polynomial h, if we restrict this problem to only max int smaller than h, there's a polynomial time algorithm for this subproblem. So this A has a running time which is given by some polynomial O of P of the input size and max int, a lot of parentheses. So if we're given some input in this restricted value problem, value h of u, then for this instance, max int is at most h of x. Right? And this is a polynomial, so this is order n to the c for some constant c, depending on this polynomial h. And so the running time of the overall algorithm is we just insert n. I'm using n again for the size of the input, as always. And max int is this, so order n to the c. And that's another polynomial, just as we discussed now, for another constant d. And so A runs in polynomial time for all x in value h of u. Okay, that's all there is to prove here. And so if this is a decision problem, then the value restricted problem is in P. If it's an optimization problem, the value restricted problem is in PO. Works both ways. It doesn't matter what the algorithm does, if it decides and just outputs yes, no, or if it actually finds a solution. So simple stuff. Now, whenever you define things, there's the slight danger that you're talking about the empty set. Maybe there is no problem that has an interesting pseudo-polynomial time algorithm. And so in the next subsection, we'll see one concrete example for a problem that is in general NP-hard, but admits such a pseudo-polynomial time algorithm, which indeed has practical value, because Sometimes in these problems, the integers that occur are indeed not too big. That's the knapsack problem. So just to recap, we've seen the decision version. The optimization version is given here again. We have these items, 1 up to n. And what we're given is the weights, which is a negative thing if you want, and then values, which is the positive thing, and some capacity. And you're trying to select a set of items, T, so that their total weight is at most B. They fit into your knapsack. It's also called the burglar problem. You're breaking into a house and you're trying to take as many valuables as you can fit in your backpack before you have to run. But if your backpack's too heavy, you can't run fast enough. Let's stay with the more neutral formulation. So you just take items of total weight at most B, but you want to maximize the value you get for them. Okay. Let's recap what dynamic programming is, just to put that in context. This is mostly for people that's seen this template in efficient algorithms. A reminder, if you've seen dynamic programming somewhere else, then you may have seen it in slightly different terminology. The essence of dynamic programming is to break a problem into small subproblems that you exhaustively solve, but where you can reuse solutions of subproblems to stitch together a solution for a bigger problem. And then there's the bottom 3 steps are very mechanic. They're always the same. So just on this concrete example, for the knapsack problem, what we can use as subproblems is restricting to the first n prime items. Instead of allowing all of them, we just look at a prefix of the items. And we also restrict the weight to be potentially less than the total weight we are allowed in the end. And then at each point in time, we'll make a guess whether or not we include this last item that we're allowed now. And that will be enough to write down a recurrence. So let's do that together. V stands for value. It's going to be the maximal value you can get in this subproblem, meaning you can only pick items up to position n prime. You're only allowed the first items, and the weight is further restricted, not B, but B prime. So we'll need some base cases. Let's see if I can fit that here. We can do the idiotic base case when n prime is 0 and I'm not allowed any items. Then the maximal value has to be 0. That might be all base cases we need, really. Let's see. If we're allowed one item, at least one, then there's 2 options. Okay. If we have, if the new item n prime fits in our knapsack, then we have the option of taking it. If it's too big, then we don't even have this option. Let's do the simple version first. And then this will be the more interesting case. So if the item n prime cannot fit in, the best I can do is to use any of the previous items. And I'm still at full capacity. I can take the same capacity, it doesn't matter. Now, if I can fit this last item, I have 2 options. I can pick the best of 2 choices. So I'm doing a maximum. And one option is the same as above. I'm not picking this new item that I'm allowed now. So again, this option. But here I have the second choice of picking this new item. So I get the value for n prime. But then for the rest of the items, I only have b prime minus the weight of this. So I have a smaller leftover capacity. I have a smaller leftover capacity, whatever is left after putting this item in, but I get the value for this item. With this recurrence, the final answer will just be in the original problem, where I'm allowed all items and the full capacity. And you can recursively fill those. Now this is the point where it makes a difference. If you've seen DP before, you'll say, yeah, I know I can take it from here. There's a bottom-up algorithm to fill a table of all those V entries, and I know how to backtrace, and you can reconstruct the solution. If none of this makes sense, then suffices to say that you can evaluate this recursion, and whenever you use a value recursively, you store it in a lookup table, so that you're never computing the same value again, which means you're only going to spend constant time evaluating any of these options when you first evaluate them. Now, constant time is the number of arithmetic operations. On a Turing machine, it would be log max int time. So let's analyze the running time. So to compute these options, in particular compute the max and the plus, log max int. Because these are numbers with that many bits, and you have to add them up on a Turing machine. We're in this logarithmic cost model. That's for one of these entries. And the number of entries in the matrix is the overall number of items, and the overall number of entries for the second component is the budget. And now the number of items can be bounded in terms of the size of the input, but B is a number that I'm specifying in the input. N is bounded, the items are bounded by the input size because I have to list the number for each of them. So I need to spend at least n bits to specify n items. But for this number B, the capacity of my knapsack, this I can just write down as a binary number. So this will be another factor. And here, it's just max int. That's the best we can say in general. So in particular, this is the pseudo-polynomial part, that we have to fill this table for all possible capacities between 0 and b. All right. Here's summed up what I've briefly sketched. The running time for this dynamic programming algorithm is polynomial in the input size and max int. And so it's a pseudo-polynomial algorithm. But you may also know that the knapsack problem in general is NP-hard. So it is one of those cases where we shouldn't expect a polynomial time algorithm, but a pseudo-polynomial algorithm is possible. This is one concrete example where this theory seems to have value, and if indeed your capacities are small, then that's good. Also, let me point out, this is a bit pessimistic in that sense that we don't care how big the values are. It's only the weights that matter, or the capacity of the knapsack. If the values are big, that's not a problem. We just compute with them and add them up. The capacity is what blows up the space of this dynamic program. So just to stress that point, that might be, in an application, this might make a difference. Now we've seen one concrete example. You can apply a very similar trick to some other problems, which admittedly are somewhat similar to knapsack. There's the partition problem. Remember, these are numbers. Can you assign them to two camps so that their sum is equal? Or making change, if you have coins and you're trying to give the smallest number of coins to make a certain total. Finding the minimal number of coins is NP hard, but can be solved with such a pseudo-polynomial algorithm. But they also have a similar flavor to this knapsack problem. Whereas for other problems, even if they're integer input problems, it seems you cannot do such an algorithm. And there's a little bit of theory to suggest why that is indeed not possible. It's just a bunch of slides. Maybe we can briefly do this and conclude with that unit. It's a very short piece. The general template in this module will always be looking at some algorithmic tools that make solutions possible even though problems are hard, and then complement that with theory to show where it does not work. In this case, the theory is very shallow, and so it's a short subsection. Nevertheless, in this short subsection, let's talk about the corresponding hardness theory, and that's strong NP hardness. The definition is simply a problem is not only NP hard, but strongly NP hard if there is a polynomial so that this value restricted subproblem is still NP hard. So even if you restrict max int to a polynomial, the problem remains NP hard. And then obviously a pseudo polynomial algorithm wouldn't help because you remain with an NP hard problem, so it's unlikely to exist. Okay. Let's briefly try to prove this. If P is not NP and U is strongly NP hard, then there cannot be a pseudo polynomial time algorithm. Okay. This means there exists a polynomial P so that this value PU problem is NP hard. That's just the definition from above. So assume towards a contradiction that A was a pseudo polynomial algorithm for U. Well, that means that A runs in time a polynomial in another polynomial and in max int. But here specifically, if max int, if x is from this value pu, then I can further bound this by p of x or p of n. And so the whole thing is a polynomial for some constant c. Running a bit out of space here. But that means I'm computing the solution for all instances of an NP-hard problem in polynomial time. So I would have shown that value P of U is in P. But we assume it's NP-hard, so that would mean P is equal to NP. And that's a contradiction to our assumption that P is not equal NP. So the assumption must have been false, and there cannot be a pseudo-polynomial time algorithm. Okay, didn't need the extra space after all. And as a last example, let's show that indeed one problem we know of is strongly NP-hard. And I'll leave it with a very simple picture proof. We show that the Hamiltonian cycle or Hamiltonian path problem, cycle is more direct, reduces to the value restricted problem of TSP, where I restrict the values to be 2 at most. And so what's the input for a Hamiltonian cycle? It's a graph. Oopsie. And the question is there some Hamiltonian cycle in this path, in this graph? Now, I'm just going to give the transformation just assigns distance 1 to each of these edges in the graph, and distance 2 to all the non-edges, those that don't exist. So there's a lot of non-edges to draw. I'm not going to do all of them. But the point is, if this is certainly an input restricted problem, all the integers that occur are 1 or 2. And so if I can find a path in this, a round trip in this graph of cost exactly n, then that is a Hamiltonian path, and vice versa. Okay? Let's do dashed lines. Come on. I might have said Hamiltonian path, I meant cycle. Right. So this is one example. It's a very simple reduction. It's the same reduction that people may have used for showing TSP is hard. And in this case, it just produces only instances with tiny numbers. I'm probably okay. I'll skip the proof this because we're running out of time. A tiny remark that's sometimes useful. You can think of strongly NP-hard also as it's still NP-hard if you force the encoding for the integers to use the unary encoding. What's unary encoding? Well, the numbers 10 would be represented by 10 ones. Okay, so you blow up your input size, which is the same, which effectively transforms the input size into max int, or a polynomial of max int. And you can show that this is equivalent. A problem is strongly NP-hard if and only if the encoding for that problem with unary encoding for all integers is NP-hard. Sometimes that's more convenient to show or more convenient to reason about. Good. So that's all on pseudo-polynomial algorithms. If the numbers are indeed small, this is often good enough. It's a fairly restricted technique, though. Indeed, the examples are listed on the slides are the only ones I know. I'm not sure if there's a second fundamentally different problem where pseudo-polynomial algorithms would work. And so we'll have to work a bit harder in the coming weeks to extend that. Good. See you tomorrow then.